Okay, the registration is on. I know that you can check it. And so I will start. As I promised you, the next, I don't understand how to get rid of this. I hope it is. Yes, it's working. Oh, so we can start by looking at these two pictures. They are the two heroes. Sorry, I have an urgent message from a colleague. So the two heroes of today's story are Girolamo Cardano, that you see on the left, and Niccolò Fontana, whose nickname was Tartaglia. And I will explain to you why that was his name, by which he is remembered in history. As you can see, the birth dates and the death dates of both, they were almost contemporary, and there was only a 2-year difference in their date of birth, but there was a considerable difference in their date of death, almost 20 years different. So it is a typical, what stands behind this story is very important from the point of view of understanding what was the attitude towards algebra that by the time of the 16th century had developed to a certain extent, just because of all what we discussed in the previous lecture about the 12th century. Now Al-Khwarizmi was known, Niccolò Pisano, named Fibonacci, was known, had written his abacus. In many universities, there were now people like Pacioli who were studying the beginning of mathematics and algebra in particular. And the search for solutions of algebraic equation had become a sort of sport. The end of the Middle Age attitude towards solving equations had become similar to the attitude that nowadays we have in front of some enigma to be solved, some kind of competition for who is the best. In fact, the story I'm going to tell you has all the aspects of a romance. Is tragic from certain point of views. It is almost spectacular and ridiculous from other points of view, and reveals what was the cradle of modern algebra. The main thing that people were still missing were complex numbers, of course. Irrationals had been digested. Roots of numbers had been digested. And so now people were freely speaking of not only of square roots, but also cubic roots and other powers. But no one could understand what was the square root of -5, for instance, not to speak of -1. Yet, slowly, by trying to solve equations, the notion of imaginary numbers came into being, because already in the treatises of these two guys, and a little bit later in the 17th century, in the book by Raffaele Bombelli from Bologna University, there was a conscious treatment of square roots and higher roots of negative numbers. The very idea of the notion of I, the imaginary unit, came only later. And the name imaginary is due to Descartes, Cartesio in Italian, and a famous sentence from one of his works, where he was saying the following: one could imagine that every equation has as many roots as its rank might suggest. So our imaginary as a root is the name root is an invention of algorithms. In fact, it's something I would like to go back to, because I forgot to tell you, but it's important. Sorry?
Prof, mi scusi se la interrompo,
Yes?
ma si sente tantissimo a scatti, cioè io non sto sentendo niente.
Oh, strano. Allora, forse...
Dice che ha tipo la connessione bassa, non so, la vedo ogni tanto sulla sua figura, compare un triangolino arancione.
Allora, forse quello che conviene fare è che io chiuda il video, tanto di vedermi in faccia non è che vi serva molto. Magari questo riduce. Let me try to see whether I can solve this problem. Interrompi video. Ok. Can you hear better now?
Sì, ora sì.
Allora, ho tolto il mio video, intanto non è che serva molto il video, anzi non so come togliermi il quadratino dai piedi, perché sta sempre lì e mi impedisce la visione dello schermo. Now, can you hear me distinctly now, or there is a change in Do you hear me now?
Sì, adesso la sento normalmente, diciamo.
E il video si vede?
No, il suo video no, è disattivato, vedo soltanto
Sì.
il suo schermo.
L'importante è che voi vediate lo schermo, il
Sì, sì,
video
sì, sì.
non serve a molto. Just a moment, I wanted to tell you something I forgot to tell you about Abu Jafar al-Khwarizmi. In the recent book I've written, I've created a dialogue in the Beit al-Hikmah, in the house of wisdom, between al-Khwarizmi and Buna Musa. And maybe it is interesting, just since I spent a lot of time in this is imagination, of course, but I tried in this way to represent what was the difficulty, the conceptual difficulty. So I imagined that, and this is possible, it's quite possible, that in the house of wisdom, Banu Musa, the son of Moses, the three brothers were all of them mathematicians, and Abu Jafar al-Khwarizmi, Abu Jafar Muhammad al-Khwarizmi, were discussing about the publication as it was at that time. It is finished because it was written, of course, with the pen. And so let me show you some part of my book at page 100. And page 100. Okay. I imagined that one of the three brothers who had the same name, by the way, was also Abu Jafar as al-Khwarizmi, says the following. Al-Khwarizmi says that he spent 10 years to write his treatise because he had an essential difference. So one of the three brothers asks al-Khwarizmi, we also had some difficulty studying Archimedes and studying the exhaustion method of Eudoxus. And we had the impression that in those marvelous geometric constructions, there was something that was missing, something very simple and fundamental that our Greek ancestors had missed, says one of the Banu Musa. And he says, what was the missing element in your case? Interrogates al-Khwarizmi. Maybe I already know, but I'm glad to hear it again. And the Abu Jafar, one of the three brothers, answers, what was missing was the concept of number. The ancient Greeks were missing a modern conception of what is a number. And al-Khwarizmi replies, this is strange what you say, because the Greeks had the veneration for numbers since the time of Pythagoras. And the youngest brother answers, yes. But what was for them a number? 1, 2, 3, and so on, the integer numbers. And they came into a crisis when they discovered the irrational numbers, themselves the Pythagoreans, as we said. So they discuss about that. And the conclusion is they wanted to square the circle. But the solution was that there are more numbers than they thought. The ratio between the length of the circumference and its diameter, which is, as we know, the number pi, is a number. And they wanted to discover something. Simply, they had to define it as a number. And indeed, it is the main contribution of one of the Banu Musa was the treatise about where he made a commentary on Archimedes, and essentially was defining the number pi for the first time in history. It was just taking the opposite viewpoint, saying, look, it is not that we have to find some clever way of obtaining this number. We simply have to say the ratio between the circumference and its diameter is a new number, the number that we call pi. And then with the exhaustion method of Archimedes, he tried to calculate approximations of pi. We simply have to calculate approximations. And by the time we also have more powerful computers, and we just know when we write in digits approximation of pi. But pi exists as a number. And in fact, it was not even in irrational numbers, it was a transcendental. And so he concludes, His Majesty Allah has created, who made everything, also created the numbers. And he has created numbers of various types. They are not, another message. There are square numbers, there are polygonal numbers as the Greeks were creating, and so on and so forth. But there are also numbers like pi. I don't know whether it was already called pi or not. I'm not aware of, but the fact is that it was clearly defined as the ratio between the length of the circumference and the length of its diameter. Then there is some joking, and next to it, Abu Jafar, Al-Azan, another of the three brothers, asked, what was, we clarified with you, what was our discomfort with the ancient Greeks? What was your discomfort with what the Greeks had done in mathematics, because algebra was a name still to be invented. We understood how it went in the West with the book Halahab. And my good friend Al-Khwarizmi answers, what was disturbing in the treatise of Jophantus, which is from many other viewpoints very, very beautiful and very deep, is that he was proposing a variety of problems. And each of these problems was treated as an independent one that has to be solved with some effort of one's talent. And there is a continuous change of scene where you can never predict what will happen. And now, he said, look, one typical example is not to Diophantus, but to a legend about Diophantus. That is the following. It was well known in the history, in the Greek history. It appears in the commentaries by Hypatias to Diophantus. Apparently, Diophantus expressed his last will that the following epigram should be put on his tombstone. And that was a sort of quiz. Translated into Italian, if you can follow, but I can translate into English. This tomb encloses the mortal remnants of Diophantus, who, quite surprisingly, told you mathematically what was the length of his lifespan. 1/6 of his life was infant. When he reached his 12th year of age, no, sorry, that 1/6 of his span was necessary in order for first beard to appear on his face. After another 1/7 of his life, he married, and after 5 years of marriage, one son was born. The unfortunate son died just surprisingly and abruptly when he had half of the age of his father. Father lived another 4 years in mourning, and then he died. So now this is clearly an equation. It's a linear equation where you have an unknown, that is the x, which is the lifespan of Diophantus. And you know that you have to take 1/6 of x, then you have to add 1/12 of x, then you have to add 1/7 of x, then you have to add 5, which is a known number. Then you have to argue that there was 1/2 of x at time of birth of his son to the death of the son, then still 4, which is a known number, and that is the sum equal x. If you solve this simple equation, you find that he lived 84 years. But you see, there was no equation with it. It was a sort of problem that was posed, and it was, I mean, it is even difficult if you do not, for us nowadays, if you do not take a piece of paper and you translate into a formula immediately the content of this sort of epigram to find the answer. If you do that in 2 minutes, you find the answer. But then our friend Al-Khwarizmi says, look, I might rephrase exactly the same problem with a different story. And he says, look, in this rucksack, in this small container, there is a certain number of grains. And I don't tell you how many they are, but I tell you the way I put them in the box. Let's say it's a box. And then he repeats exactly the story of Diophantus. First, the sixth part of the whole lot, then the 12th part, then the 7th part, then I put 5 grains, then half of the total, and finally 4. The question is, how many grains are there in? Of course, as many as the years lived by Diophantus. It looks like a stupidity, but you have to understand that from the point of view of the Greeks, these were independent problems. They had made a lot of advances in geometry, but from this point of view, they were still missing something. They would consider these two problems as different problems that strangely have the same solution. Of course, they are simply complicated way of describing the same equation, but the notion of equation was still missing. That is what they are discussing in this sort of nice conversation. And at the end of his discussion, he says the important thing was to discover that you don't have to formulate the problem like a tale in this way, but you have to say it in a more abstract way. And so he explains essentially what he has done. He says that the number that we don't know, I named Gizr, which means root in Arabic, or alternatively, Sai, the thing. But what has survived is Gizr. Then we have the known things, which he called Diram. So Diram is a special Arabic name that he used for that, and is what, let's see, I have forgotten what Diram means. Diram, it's very important. It was the monetary unitary of that time in the Caliphate. So the known thing is what he calls Diram, is the coin, the coin. And then he has invented a special name for the square of the unknown, of the root. There is the root, the square of the root that he calls mal, and then there is the diram. And at this point, he asks, do you understand now what is an equation? And the three brothers answer at the same time. It is a relation between diram, girs, and mal, namely unknown, square of the unknown, and known term. He never wrote formulae. He expressed in words the relation between diram, girs, and mal. But it was already a very, very big advance, because he understood the level of abstraction. You can rephrase every equation by writing a relation between every second order equation by writing a relation between gives him out. And then he studied a way of solving that. So you see, the second order equation had come to that point. And of course, there was still a big problem there. The big problem being, let me see, I come back to where I was. Yes, here. The story of Girolamo Cardano and Niccolò Fontana. Second order equations were solved, but so far people were accepting only solution, let's say the following way: real numbers. Imaginary solutions were not yet considered because they were real. So you would say this equation has no roots. But that were the equation of degree 2. At the beginning of, in the middle of the 16th century, time of Cardano and Fontana, the obvious questions that had arisen was, can we find a solution for higher order equation? And the next one, of course, is the cubic. So the story goes the following way. The question was debated, and apparently the first person who was able to find some kind of formula in order to solve the cubic equation was someone, professor at the University of Bologna, named Scipione del Ferro, who died in 1526. But just because of this almost mystical way of looking at the solution of equations, he never published this result. He not even told other people about it. He kept it as a secret. When he died in 1526, he thought that he should tell this secret to someone, and he called to his deathbed his pupil and student Antonio Maria Fiore, who learned from Scipione del Ferro the formula to solve probably some, not necessarily all, of the cubic equation. And what was the behavior of Antonio Maria Fiore? It is very typical of those times. He was not publishing an article, but he wanted to make money out of that. And so there was someone who had appeared to be able to solve certain problems, cubic type, was Niccolò Tartaglia. By that time, someone was 27 of age, something like that. So, according to a tradition that was customary at the time, Antonio Maria Fiore made a sort of challenge. It was typical to go to a public notary, publish a challenge saying, I can solve problems of this type. If someone wants to challenge me on that, we agree that on a certain day we will meet in front of the public notary in some place, Typically, it was in some square or in the court of some university. And then each of the two opponents would give a list of problems to his opponent. And they had some time. The public notary was checking that everything was clear and without, without any cheating. And the two opponents would sit at their little table, not far from the public notary, and they had a certain number of hours to find the answer, to write it, and then give it to the public notary. So Antonio Maria Fiore challenged Tartaglia with problems on the cubic equations. And Tartaglia did the same with him. But unfortunately, Maria Fiore was not so smart as he thought to be, while Tartaglia had separately discovered the solution formula for the cubic equation, already reduced to the standard form. By shifting the variable, you can always reduce a cubic equation to have only the third order term that you can, of course, rationalize, normalize to 1, the linear term and the known term that are respectively called P and Q. And by a shift, you can always delete the quadratic term. So this is the canonical normal form. He had discovered that, and then he had found the solution formula. Now, what happened is that Tartaglia solved all the problems put by Maria Fiore, and Antonio Maria Fiore solved none of the problems posed by Tartaglia. This produced a certain amount of money. The bet, essentially, they had posed the two opponents on that challenge, but more than that, made Tartaglia extremely famous. The news spread that someone by the name of Tartaglia was so smart that he could solve all possible cubic equations. Now, we have to spend 2 words about the life of Tartaglia. Tartaglia, as we know from this picture, was born in Brescia in 1499. And in all pictures of him that remain, he's always shown with a beard. That is true of Cardano as well, but for Tartaglia, there is no exception. There was a special reason for that. That is also the reason why Tartaglia is named Tartaglia. His real family name was Fontana. Fact is that in the terrible years, the beginning of the 16th century, when there were all the wars between Spaniards, between the Emperor Charles V and the French King François Ier, the Francis I, all this war were as battlefield Italy, and the main prize of who would win was the conquest of Milan. Milan was extremely important, both for the French and for the Spanish, the German Spanish, the Habsburg. So the French people, the French at the beginning had prevailed, and Milano was, in fact, had become, after the death of Ludovico il Moro, the last independent Duke of Milano, had become a protectorate of France, and that was also the reason why Leonardo da Vinci went to France, where he lived the last years of his life in Amboise. If any of you has ever been on the Loire, where there are all these castles in Amboise, there is still the house where Leonardo lived and produced his last works. Okay, so during these happenings, as you can understand, Tartaglia was a boy at the time. There was the very truant and famous sack of Brescia, perpetrated by the French soldiers, who made a real massacre in that storming of the city. And the poor Tartaglia with his mother was hiding in a church, but a rough French soldier found them, and he didn't kill the boy, but in this context, he received, maybe without true will to do it, but you can imagine what happens when there is a storming of a city, when these soldiers that want to get precious things also from churches can do. He received a beat, and it was how to say, with his sword, the French soldier created a damage to Tartaglia's face. And because of that, in order to say to hide the consequences of this happening, he was always wearing a beard. But he also had problem in speaking, because he had his mouth damaged by this. And that is the reason why he was called Tartaglia, because he had some difficulty in speaking. Okay, so he became so famous after that. And what happened next is that Girolamo Cardano, whose life was also very adventurous and filled with a lot of crises and happenings, Cardano received news of this fact that Tartaglia had solved the cubic equation in some way. And he was very curious to learn the formula. So Cardano, first of all, you have to know, was a different origin. Tartaglia was of a humble origin in the Republic of San Marco, while Cardano instead was of almost a noble family. His father was an important lawyer, and he was among the friends of Leonardo da Vinci. His father had was relatively rich. He had money and properties, and he was and he generated his son Cardano as a so to say illegal son, because he was not married with the mother of Cardano. But later he married her and made her his wife. Cardano had an excellent education, was a fine Latin speaker and writer. He was competent in all sorts of things. He was, first of all, a physician. He had received a degree in medicine from the University of Pavia. He was an astrologer. He could read Greek, and he had read Claudius Ptolemy, but he was using it to make astrological predictions. At the time, every one of these figures were trying to make money in some way. It was a very, very unstable time. They were very unstable times with all these wars, and not very happy times as we usually think of the Renaissance. It was Renaissance, but there were wars, were disasters, and people tried to survive. Out of the universities that were dominated still by the church, the new scholars were surviving in all sorts of things, with all sorts of tricks. So Cardano, for instance, tried to make money with astrology, where he was saying the most stupid things from not too smart people who believed in this sort of stupidities. He was studying the theory of probability, also published something on that. And he thought that using the calculus of probability, he could gain money in betting. So he was a gambler. And actually, what he succeeded in doing was to dissipate all the properties and money he had inherited from his father. He was a strange man. So this is in order to very, very smart, but with a low moral. He had also a lot of suffered many things in his life, in particular from his children. One of his children was even executed as an uxoricide because he killed his wife, who was clearly a public woman, as they used to say by that time. He had many reasons to be quite against his own wife, because she was not a very nice lady. But killing her was an exaggeration, and he was condemned to death. The other son of Cardano, on the other hand, was a thief and robbed his own father. So, I mean, how to say, the landscape of the Renaissance is quite turbulent. So we come to what Cardano did. Cardano wanted to learn the formula from Tartaglia, and he devised the following. He asked Tartaglia to come and visit him in Milano, promising to him that he would introduce him to the Spanish governor of Milano. It was one of the Grande de España. His name was let me see. It was Alonso something. I cannot remember his exact name at the moment. Okay, I will find his name here in my own book. But what happened is that yes, Alfonso Davalos. That was the name of Alfonso Davalos. Here it is. It was the name of the Spanish governor of Milan. So he pretended with Tartaglia that he would introduce him to this very powerful man. He was the acting deputy of the Emperor Charles V in Milano. But it was by no means true. He didn't have any way of introducing himself, not even Tartaglia, to the governor. That was a lie. And he was very, very, very careful to invite Tartaglia precisely at a time when he had information that Alfonso Davalos was not present in the city. So it was a sort of trick by which he attracted, by means of which he attracted Tartaglia to Milano, and then he treated him very nicely and told him that governor would come, but in those days he used all means to extract from Cardano, who was a simpler person, his secret. Finally, Cardano, so to say, surrendered to his guest and told him the formula. But it is interesting to see how the formula was given. It was given as a poem. And this poem he had learned by heart, and in this way he could solve all the problems that he was posed by remembering the algorithm, we would say, to find the root. Now, the formula, you probably know, is the famous formula that is given here, where P and Q are the two coefficients, and the root is given by the sum of the cubic root of these two combinations with plus and minus of the known term plus the other square root of this particular combination. Now, look at how this formula was translated in a poem. Thus, I will not translate into English, but those among you who understand Italian, I think that today you are all Italian, so I have no problem. But also our Spanish friend can understand it, I'm pretty sure. Although no one of us would be able to translate it into a formula. Quando che il cubo con le cose appresso si agguaglia a qualche numero discreto, trovano due altri differenti in esso. So due altri differenti in esso means the linear and cubic term. Poi terrai questo per consueto, che il loro prodotto sempre sia uguale al terzo cubo delle cose netto. E il residuo poi suo generale dei loro lati cubi ben sottratti varrà la tua cosa principale. E la cosa principale è the unknown. E nel secondo de codesti atti, quando che il cubo stasse lui solo, tu osserverai quest'altri contratti, del numero farai tal parte a volo, che l'una in l'altra si produca schietto. Il terzo cubo delle cose in stolo, delle quali poi per comune precetto troverai i lati cubi insieme giunti e cotal somma sarà il tuo concetto. E il terzo poi di questi nostri conti si solve col secondo, se ben guardi, che per natura sono quasi congiunti. Questi trovai, e non con passi tardi, nel 1504-30, so he discovered this formula 1534, con fondamenti balzanti e gagliardi nella città dal mare intorno Centa. E la città dal mare intorno Centa clearly is Venice. So this is the way they were writing a formula. It is really very much surprising. It is similar to in a way, it is similar to what Diophantus was doing, but it is different because it is not a story about the years, how many years I lived on 1/6. And this is clearly a way of telling you a mathematical formula. But it was still written in words, not written in symbols. So what happened after is that Cardano learned this, and differently from Antonio Maria Fiore, who was a complete idiot, he had a very good student that was Lodovico Ferrari. And together, Cardano and Ferrari verified probably Cardano formula several times. In the meantime, Tartaglia went back to his own city of life, that was Verona, in the Repubblica di San Marco. They verified the formula, convinced themselves that it was right, and they tried to derive, as they did, the analog formula instructed by the way Tartaglia had done for the cubic one. They were able to solve the fourth degree equation, also putting it into a normal form by killing the cubic term instead. Then what happened is that the story about the fact that Scipione del Ferro had given transmitted the formula to Antonio Maria del Fiore became known. And that was the excuse, since other knew, was the excuse for Cardano to forget his promise to Tartaglia that he would never disclose to anyone the formula for the cubic equation. And on the contrary, what happened is that Cardano wrote by himself the famous book Ars Magna that we can see here. This is the frontispiece of his book, Hieronymi Cardani, prestantissimi mathematica philosopher, as I cannot read further, Artis Magnae sive de regulum algebraicis, etc., etc., opus perfectum, blah, blah, blah. That book contains the recipe to solve both the fourth order equation and the third order equation, as it had been discovered by Tartaglia. But Cardano was adding a new formula for the fourth order. So the reaction of Tartaglia was quite violent. He cited Cardano in a court, but you have to understand that it was had to be an international trial because the Duchy of Milano and the Republic of Venice were two different states at the time, so it was not so easy. And there was even something worse that happened. Ludovico Ferrari at this point challenged Tartaglia with problems and humiliated him. In this challenge that happened on August 10th of 1548 in Milano, the Tartaglia was not able to solve the problem posed Ferrari, who treacherously had introduced also fourth order equations because he was able to solve them. And for some reason, Tartaglia lost the challenge with Ludovico Ferrari. And that was not only moral humiliation and severe consequences, because the University of Brescia declared that he was him cancelled from his chair of mathematics there. So he had to live the rest of his life still quarreling with Cardano, but he had to live being a private teacher. He lived in Verona, as I told you, after that. And it was surviving giving lectures, private lectures to students. So Cardano was really a strange figure. He was very smart, but he suffered a lot in life, but he also inflicted very, very unconceivable pain to his opponent Tartaglia with no good reason. I mean, at a certain point, Cardano also had to flee from Milano, and he was nominated professor in the University of Bologna by the Pope, and he wrote many things about many topics, but he came in a very dangerous situation in the year 70, I think. Let me check. What was the year when he was imprisoned by the Inquisition? At that time, it was the year 1570. He was imprisoned by Inquisition with the charge of heresy, which, as you know, could very well end up with being condemned to be burned alive. But he came out of this because eventually the Pope was protecting him to a certain extent, and he agreed to burn a lot of his books that were considered heretic. So he came out of it, went to Rome, and still lived another 6 years in Rome under the direct protection of the Pope. That had some esteem of him, in particular as an astrologer. So this is the story how this fourth and third order equation were solved, and that brought into being also when a more mathematical notation came to be utilized. That happened very soon, as I told you, with the treatise of Raffaele Bombelli a few years later. Bombelli, let me see, should have it here. No, I don't have it. Okay, in any case, Raffaele Bombelli published in Italian, and he clearly talks about square roots of negative numbers freely. It does not introduce the notion of the imaginary unit I, which is something that I told you was more or less imagined by Descartes, but was introduced with the present notation and only in the 18th century by Euler in St. Petersburg, where he introduced the notation we still use for a complex number x plus iy. He also introduced the notation for the exponential, the number e, which indeed is named the Euler number, and he introduced the notation for the exponential notation for cosine and sine. He is responsible for such basic formulae like e to the power ix is cosine x plus I sine x. Okay, but it is an obvious story that it is a predictable thing that after the third and fourth order, the scholars of the time would inquire the fifth order and the sixth or the seventh order. But of course, the next one was the fifth, and that was a barrier, because although explicit solutions of fifth order equation could be easily constructed, a general formula for the fifth order equation no one could find for 2 centuries, almost 3 centuries, until the time when Galois demonstrated that the generic fifth order equation cannot be solved by radicals. And so all the successive orders. The formulae in terms of roots stop at the fourth order. And the reason is really very profound, as you possibly have learned, is the fact that if you come to group theory, and that was the genius of Galois to rephrase the problem of algebraic equation in the language of group theory that was just beginning. It was in its infancy at the time of Galois, and Galois was one of those who made it progress quite extensively. The question whether an equation contains or not, admits or not solution by in terms of radicals depends on the group structure of what we now call the Galois group of the equation. If that group is solvable, then there are solutions by radicals. If it is not solvable, there are not. In particular, if it is a simple group. And the reason why the third and fourth order equation are solvable is because the most general Galois group of these equations of third and fourth order is always a subgroup of the permutation group of order 3 or order 4, and these groups are solved. So all the subgroups are also solved. As you see, the question of algebra is a very deep question, and at the same time is fundamentally related with the question, what are the numbers? The numbers were for the ancient only the integer numbers. Then there was the discovery of the irrational numbers. Then came some instances of what we now call transcendental numbers. But the conception of what we now call, on one side, the real numbers, on the other side, the complex number, arose very slowly and could not be disconnected by a more abstract understanding of algebra. Nowadays, we have a clear understanding why every equation of any order can admit complex solutions as many complex roots as is its order. The reason is that the field of complex is algebraically closed, while the field of real numbers is not algebraically closed. And it was the genius of Galois to introduce the very notion of field and extension of field, or in Italian we have two words, campo, or the other word is corpo. In English is just field. But in order to do that, you had to develop the theory of algebra much more extensively. So it was already in the 17th century that D'Alembert advanced the fundamental theory of algebra, namely that every equation of order nth possesses n roots. But what these roots are was not absolutely clear. And there was no formula by radicals to extract them. Indeed, for the fifth order equation, the answer came only in the second half of the 19th century, which was the answer provided by Felix Klein, who studied the fifth order equation in relation with the icosahedron group and its subgroups, and eventually found the solution of, it is not true that there are no formulae for solution of higher order equation, but these solutions are expressed in terms of transcendental equations. And in fact, the solution of the fifth order equation by Felix Klein represents the roots in terms of hypergeometric functions of a certain type. Hypergeometric means something that is eventually by a series, convergent series, if possible. But obviously, it is not an algebraic number. Sorry, it is not an irrational number. It's not expressed in terms. It is algebraic because it is the solution of algebraic equation. The numbers that are algebraic are not necessarily all the possible transcendental numbers. There are transcendental numbers that are not algebraic. And the typical example is, for instance, the Euler number E or pi. They are defined intrinsically, but they are not the solution of an algebraic equation. They are not the roots of an algebraic equation. Otherwise, they would be irrationals, not transcendental, and not and not even transcendental, but algebraic. So the question, what are the numbers, is what are the roots of equation, is connected with the question, what are the numbers? And eventually, the notion of what are the numbers was refined completely only in the very last part of the 19th century. It was refined with Frobenius' theorem about division algebras. So, taking an algebraic viewpoint, you say you have this hierarchy of construction of algebras over the basic field of real. So first you have to come to the notion of real numbers, and then you come to the notion of algebras over the real numbers. So objects constructed in terms of real numbers, for instance, for the complex, the real and imaginary parts, in such a way that you have an object. In the case of complex number, is the pair of real numbers, and these objects admit the structure of an algebra. Namely, they can be summed, multiplied, but also divided. There is also the inverse, and that is called the division algebra. If in addition you add the request that there should be a norm, namely what we call for the analog of what we call the norm of a complex number, the root of x squared plus y squared, or the square norm, x squared plus y squared, which is a real number associated to every complex number. Then, if we do that, you can argue what are the possible division algebras. And nowadays, thanks to Frobenius' theorem that was demonstrated by Frobenius at the very end, towards the end of the 19th century, we know that there are all the others division algebra are isomorphic to one of these three, namely the real numbers, the complex number, the quaternions, and the octonions. Octonions were the last to be discovered. They form an algebra which is not associative. It's an algebra, but the product of x with the product of y times z is different from the product of x with y product with z. And the difference between the two products is called the associator. The associator, like the commutator, is something that can be zero or not. Complex numbers are abelian, so that all commutators and products are zero. The quaternions are not commutative. They form a non-commutative algebra, but it is an associative algebra. The octonions, instead, were the number of as you know, the quaternions have three imaginary units that satisfy the famous quaternionic algebra, which is a rephrasing of the Lie algebra of SU2. On the other hand, the octonions that were the last to be discovered in the second half, but at the beginning of the second half of the 19th century, they were independently discovered. The quaternions were discovered by Hamilton, the same who discovered Hamiltonian mechanics. On the other hand, the octonions were independently discovered by a friend of Hamilton, who was not even a professor or a professional scholar, he was a lawyer, and by the famous British mathematician from London, Arthur Cayley. Both of them came to the discovery of the octonion numbers that are sometimes called the Cayley numbers. But besides after the octonions, there are no more division algebras. So nowadays, we probably know all possible numbers. But this story tells you how difficult it was to come to the very notion of numbers, proper notion of numbers, the proper notion of equation, and finally to the abstract construction of algebras. You see that in the Renaissance time, the way of writing an equation was still given by writing a short poem. This should be emphasized in order to understand how the process of abstraction was slow, also with very smart people like Cardano and Tartaglia, like those who came before. They were all in their own age extremely smart people, but the process was very slow because we are humans and we are born in our environment, physical environment, and the capacity, the attitude to formulate abstract conceptions is something that now that it has disclosed becomes easier and easier for the newer generation. But it required a lot of effort to arrive to such abstract concepts. And in fact, now we will jump over the 17th and 18th century, and we will come to the beginning of the 19th century with the next lecture that will deal with Galois. Galois is a genius, very unfortunate genius. His story is moving. Died at the age of 21 in a duel, but he suffered all sorts of scorns and pains, as one might say, imitating the way of phrasing of Shakespeare. But what is at the heart of his work goes much beyond the importance in algebra, much beyond its application. He developed many ideas that are just in one paper that was published 16 years after his death. Well, 14 years after his death. It was really incredible mind, and he saw things much beyond his time. He personally produced this level of abstraction, of abstract thinking, that made him, that enabled him to translate the problem so many people had considered, that of solving equations, into a problem completely different. The problem of studying the structure, algebraic structure of the group of symmetry of the equation that nowadays we call Galois. And not only that, he understood that the property of the solutions were hidden in the properties of the group of symmetry. So he not only introduced new elements in the theory of groups, but he understood that the group is the real essence of things. the same group can be applied to many different situations, can be the symmetry of many different things. But all the things that admit that group as symmetry will have common features. And that is the way, the new level of thinking. And this is the level of thinking that comes in our modern episteme, where we think that all interactions in physics are manifestation of symmetry, and that the forces of nature can be described by connections on principal bundles that have a certain group structure. And so all the properties of strong interactions depend on the fact that is a gauge theory of SU3 and that it is unbroken symmetry. The unbroken symmetry is what produces the confinement of quarks, so it is at the heart of the world as we see it. While the weak and electromagnetic interactions are also non-abelian symmetries, but they are spontaneously broken, and this spontaneously broken mechanism is what gives mass to the W and the Z and produces the weak interaction as we see them. And this breaking mechanism is provided by the Higgs field. The Higgs was discovered experimentally only in 2012, although it was predicted 50 years before by Brautengler and Higgs. But none of this basic principle of physics that allow us to understand the structure of the universe now as no one had done before could ever be even conceived without the notions of groups, without this developing in algebra, and in particular this big jump in the abstract thinking is due to Galois, whose paper and whose life we will analyze next. I'm just hesitant to start the discussion of Galois, but maybe we can, because we have still half an hour. So before plunging into the details of Galois' life that are by themselves extremely interesting, let us see what was Galois' idea. So Galois started from the recognition that the roots of an nth order equation exist because of D'Alembert theorem in the complex field of numbers. So here comes the abstraction. He said, let us simply deal with them. As you can see, epistemologically, this is very similar to what 800 years before, almost 800 years before, exactly 800 years, no, even 900 years before, the Banu Musa had done in Baghdad, when they had turned around the Greek point of view, how can we square the circle? And the answer was, you don't have to square it. You simply have to admit that there exists a number called maybe pi, that is the ratio. So similar to that, Galois' viewpoint is the roots exist. Let's give them a name. We call them alpha 1 up to alpha n, for instance, where n is the degree of the equation. And now Given this name, now we can do the following. We start from the field of real numbers, and now we consider the following. If you take the rational function of a real number, you still are in the field of rational numbers. Okay? If you take a rational number of a real number, rational function of a real number, so rational with the integer coefficient, with a rational coefficient, but the unknown element out of which you make polynomials, the variable of the polynomials is real number. Okay, and you simply define some numbers in the real numbers, because a rational function of a real number is a rational number. Now, let us imagine that we have the field of reals, and you take rational functions of the roots of an equation. Generally speaking, these rational functions of roots that are not real numbers will not be a real number. In fact, typically lies in the field of complex number. But he asked himself the following question. The set of real or rational function of the roots has not the width of all complex numbers. It makes by itself a new field, which is smaller. It is larger than the field of real numbers, but it's smaller than the field of all complex numbers. So let us inquire how we can define a field. What we have to do is that we have to respect the field operations. If we call P the rational function of something, and we make a new rational function, then the product of rational function is a rational function. The sum of rational function is a sum of rational function, and the inverse of a rational function is a rational function. So we see that rational functions by themselves form a field. But he was now saying, look, but this field should be considered with closer view. Namely, you can make a permutation of the roots, the unknown roots among themselves. So you can take, if you are in degree n, you have the group of permutation of n objects, the symmetric group of order n. Now, you can say that the action on the abstract element A, which is a rational function of A1, An, of a permutation, is the rational function of the permuted roots. Where you had alpha 1, you put in the same place in the rational function, which is a ratio of two polynomials, you substitute the permuted element, etc. etc. Now, you obtain a new object. Now you should ask yourself, what is the group of symmetry of this field? The field of rational function obtained by adding n roots. Well, it is the set of roots, a set of permutations, sorry, that respects the field operation. Namely, if you take the sum of two rational functions of the roots and you apply the permutation, you should have that this is equal to the sum of the two rational functions to which you have independently applied the permutation. Not all permutation will have this property. So not all the elements of the symmetric group will be symmetry of this new field. And similarly for the product, the permutation acting on the product of two rational functions should be the product of the permutation applied to each independent rational function of the roots. So it was in this way defining new fields by the addition of a root or several roots. For instance, it is simple to see that if you take the real numbers and you add to the real numbers the square root of 2 and all rational function of the square root of 2, you generate a new field. But this field has a rather small group of permutation, because if you permute square root of 2, you send square root of 2 into minus itself, for instance, then everything remains as it should. But you cannot make a permutation of square root of 2 with roots that are not expressed as square root of 2 and so on. So the group is rather small. In fact, it's only Z2. It's a very simple field. But fields that are obtained by adding the roots of a higher order equation are more complicated, have more complicated group of symmetry. This group of symmetry is called the group of Galois of that equation. And Galois proposed to study the symmetry group of the equation, the Galois group. And he arrived at the fundamental theorem that tells you when an equation is solvable by radicals. This theorem states that it is solvable by radicals if the Galois group, it was not using his name for this group, but this is what posterity does. If the Galois group of the equation is solvable. In fact, the name solvable for groups of this type that I'm going to tell you precisely comes from Galois theorem. If the group is solvable, the equation is solvable, and vice versa. What does it mean to be solvable? It means that it contains a chain of normal subgroups. So the group contains a normal subgroup of maximal normal subgroup. That maximal normal subgroup contains in its body, in its guts, another normal subgroup which is maximal, and so on and so forth, up to the very end of the chain where you get the last group is the identity element. This is a solvable group. And it is just because of this solvability that the equation is solvable by radicals. The very opposite of a normal solvable group is a simple group, namely is a group that has no normal subgroups. Okay. If you will follow my course on group theory next year, all these notions you will absorb mathematically. So at this level, what I want, before plunging into the biographical details of Galois life that are by themselves very important, I want to emphasize what was the algebraic revolution, I want to make an epistemological analysis of his results. I would like to emphasize the first, the list of these 5 points. The first point is that first of all, he changed perspective. And rather than analyze the property of static mathematical objects, like an equation is, like a root is, he emphasized the relevance of the transformation that we can operate on them. So the dynamical viewpoint in mathematics. You focus not on the individual object, but on a class of objects and on the operations that you can make on these objects, the transformations. So this is already a Copernican revolution. Instead of looking, as people had done for centuries, at the individual mathematical objects, you start analyzing the properties of transformations on the objects you study. The secondly is that he put to the forefront the notion of group. The transformations one can consider are combined together by an operation. The product, and with respect to that operation, they form an algebraic structure, the group. This was more or less implicit in the previous work done on permutation groups, so-called substitution groups, as they were called, by other mathematicians, in particular by Lagrange, by Laplace, this continued also after Galois' death with other mathematicians like Liouville, considering thus it was pursued this viewpoint on the substitutions by our great mathematician, Italian mathematician Enrico Betti, but later. But the fact is that the abstract notion of group was not yet clearly singled out. In fact, the present day definition of what is a group abstractly had to wait until the middle of the 19th century with Cayley, that almost arrived at the abstract definition. But I say almost because his actions are not complete and in fact are inconsistent, because he was not singling out, he was asking in his definition that every element should admit essentially an inverse, but he was not emphasizing the need that this inverse should be unique. And that is an essential item in defining an abstract group. You can come to inconsistencies, logical inconsistency, if you do not assume that. So even the very pure definition, abstract definition of what is a group, had to wait until the second half of the 19th century, and then was completely perfected by people like Frobenius, by Schur, and living already on the boundary of the 2 centuries. And continuous groups had not even been discovered yet. They were discovered 40 years later by Lee with the transformation groups. And they came into perfect being only with first Lee and then Keeling and Cartan, very end of the 19th century. So intuition of Galois was extremely early. He understood that the notion of the group is the central. Thirdly, he put into evidence that once a group is introduced, its action, originally defined on something, the roots in this case, can be extended to something else, the field extension K. This was the beginning of representation theory, which will concern us a lot. So, in some sense, with the way he defined the action of the group on rational function, he was the first to conceive the idea of a group representation. The abstract group is unique, but its representations are many. And in fact, all possible representations of a group are encoded in its own structure. That is what we know today. He had not yet reached that point, but he was coming to it. Next, by means of the concept of automorphism, he showed that a given group which acts on some space V, the extended field, the field extended with the roots in this case, the most important things to study are the property of objects contained in V that are left unchanged by G transformation. It's the beginning of the theory of invariance. It's the beginning of the theory of what we consider the most important item in groups. We devise groups in order to mold them out. We know, for instance, that chromodynamics, quantum chromodynamics has SU3 symmetry, acting on the quarks and the gluons. But what are the physical states? Are the colorless ones. Only those that are invariant are physical and exist in nature. The quarks are confined inside just because they carry color charge. So the whole idea that the invariance, so the largest is the group, the smallest is the number of invariant things against them. But the physical things are precisely the invariant objects. And so the knowledge of the invariance is coming to be, both in mathematics and physics, is the knowledge of true objects. The others are artifacts because they are not invariant against the symmetry. The fifth point, last but not least, by means of his very theorem, he showed that the key information about the structure of a mathematical object, in this case, the algebraic equation, operated on by a group of transformation G, in this case, the Galois group acting on the roots, resides in the algebraic structure of G. In this case, the equation is solvable if G is solved. So as Vi said, when you want to study a problem of any kind, the first thing to do for you is to study its symmetry. And the structure of its symmetry will be the structure of the object you want to study. Galois was the first to have this intuition. And its example was an example very fertile. The developments in 19th century mathematics were initiated by studying Galois theory that became available only by the publication from Newville only in 1846, 14 years after his death, and slowly became knowledge about this theory developed in France and was transmitted to other countries. And all the important mathematicians that made the most important discoveries in this very fertile and productive half of the century were directly or indirectly influenced by the work of Galois, by his ideas. They extended it. They extended to new objects. In fact, for instance, Lie was motivated to introduce his group of continuous transformation by his desire to study the differential equation with the same sort of weapons by means of which Galois had studied the algebraic equations. The influence is direct and testimonial. Lie came to that because he was in France, we will talk about this, in the 70s, and he had the conversations both with Darboux and with Camille Jordan. And Camille Jordan, the one of so-called Jordan lemma, which is completely wrong pronounced because Jordan was a Frenchman, not an Englishman. And so we should say Jordan lemma, not Jordan lemma, or lemma di Jordan. Camille Jordan was the first to study very deeply Galois theory and published a book. And Lie was in Paris and absorbed ideas of Galois from his conversations with Darboux and Jordan. The same did his friend Felix Klein, who was with him at the same time in Paris. I will mention that in the next lecture. And he came to another extremely important development, this time in geometry. While Lie was applying his newly developed group ideas to the field of differential equations, Klein came to application of his ideas to geometry, and he showed that, or showed, as you prefer. I mean, nowadays people say more frequently showed, but the correct past tense in English is show. Showed that geometries are also classified. There was this long querelle about Euclidean and non-Euclidean geometry. Finally, with their Langen program of 1872, Klein came to the classification of geometry as the study of invariant properties of figure with respect to group of invariants. So Euclidean geometry is simply the study of the properties invariant under the Euclidean group made by the transformations of rotations and translations. But you have conformal geometry. You have projective geometry, where the group is larger, and it is the group of invariant properties with respect to the larger conformal group. But you have other geometries where the Euclidean group is substituted by an elliptic group or a sorry, I have a message, but we are also at the end. I just okay, I answered the urgent message. Next time we will discuss the human aspects of unfortunate Galois life. That in this respect is one of the main goals, to understand how conceptual revolution were actually created by talented minds, okay, and what was the cultural environment of the time, and then we proceed. Okay, so I leave you with this thought. I wish you a nice evening, and if you have some urgent question, I can answer, but not too long, if possible, because I have an urgent call in a few minutes. Do you have questions?
Io no, per me è tutto chiaro, grazie.
Va bene, va bene.
Anche per me, grazie.
Anche per lei, benissimo. Allora ci rivediamo mercoledì alla solita ora. Vi auguro un buon pomeriggio.
Va
Anche a
bene,
lei.
anche a lei, grazie, arrivederci.
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 Arrivederci.